Good morning, everybody, and welcome to the last session on stellar, the theory of stellar pulsations. Well, we have dealt in the last few days with the linear stability of linear adiabatic, linear non-adiabatic stability of stellar models, which we have previously calculated or constructed, and now finally, as a so-called as a summary of what we have learned in the last few days about stability, about the way how to derive this stability, the various instability mechanisms which operate in stellar envelopes. I would like to comment on or to report on a very recent study of a group of stars, which is a group of very luminous and massive stars in the HR diagram, which are the so-called yellow hypergiant, of which the star Rho Cassiopeia is a prominent member. Actually, you can see Rho Cassiopeia with naked eye. It is a star which is visible in the night sky. So I would like to comment on a study, on a stability study of this group of yellow hypergiants. Well, these stars are found to be variable both spectroscopically and photometrically, and they show indications for mass loss in the past centuries. So they have some remaining gas and dust around them. And this remaining gas and dust indicates that they have undergone phases of mass loss in the previous, say, 100 or several hundred years. So they show indications for mass loss during some outbursts for Rho Cas. They have reported outbursts in the last century, in the 20th century. Several outbursts have been reported. And currently, well, they are at least moderately spectroscopically and photometrically variable. The parameters of this star, we take the parameters of Rho Cas here, is luminosity is rather high, it's 10 to 5 solar luminosity. The temperature is moderate, it's 7,000 K, and the chemical composition is rather normal, 74% hydrogen, 24% helium, and a solar metallicity of 2%. The mass is given by the observers to be about 24.1 solar masses. Of course, the mass is the parameter of star, which is the least accurately known parameter. So once we consider the stability of that group, we take the parameters of the observed parameters of Rho Cas and take the mass as a free parameter and vary the mass between 50, this of course a very, very high value, and the lowest value we could construct a model for, which is around 19 solar masses. So we take a series of envelope models with the mass as a parameter, a free parameter varying between 19 and 50 solar masses. Okay. So let's consider now the instability or the stability of this group of stars, the yellow hypergiants, and we will find an instability for these objects. And well, it has been known for a long time that these stars show outbursts and they seem to be unstable. And people have argued that the adiabatic index falling below 4/3 is the reason and the cause of this instability. So the common opinion is gamma adiabatic, the mean value of the mean of gamma adiabatic falls below 4/3 for these stars, and this is the cause of variability, and this is the cause of the outburst for this group of stars. Okay, in particular, let's address this question whether the common wisdom about these stars is really true. Okay, we consider now a sequence of models with masses between 19 and 50 solar masses. So let's go and let's consider first the structure of these stars, of these stellar models. So we go and consider first how the structure of these stars looks like. Well, first of all, let's consider the density structure. So in the following, all these diagrams will have some models. The 50 solar mass model will be denoted with a dash dotted line. The 30 solar mass model will be denoted with a dotted line. The dashed line is the lowest mass of 19.1 solar mass, and the full line is that which corresponds to the object with 24.1 solar mass is appropriate according to the observers for Rokas himself. Okay, what we see for the density structure, well, here the density is given on a logarithmic scale as a function of relative radius, and what we observe is that there is an extended envelope with extremely small densities. That's true for all these stars. And then we have a stellar core where the density increases sharply, and which the core contains almost the entire mass of the star and does only occupy only a small fraction of the volume of the star, whereas the envelope extends almost over the entire volume of the star and has only a small fraction of the mass. So all the mass is concentrated in the core and does not occupy a big volume, only occupies a small fraction of the volume, whereas the envelope does not contain, only contains a very small mass and extends over the entire volume. This is true for all these stars, but the behavior becomes more pronounced if we go to lower masses. So this is the highest mass, 50 solar mass, and this core envelope structure becomes more pronounced once we decrease the mass down to 19 solar masses. So this has implications for the ratio of the thermal to the dynamical timescale. Well, here the thermal to the dynamical timescale is plotted as a function of relative radius, and we observe, well, that of course, like in any star, this ratio increases in the interior of the star, so the star will behave adiabatically in the core, and at the surface, this ratio is of the order unity or less. And the non-adiabatic domain of the star, well, here the 50 solar mass, the 30, 24, and 19 solar masses, the domain where the star has a small thermal timescale, this domain increases once we decrease the mass. So this star should be closer to the adiabatic limit than this star, and the thermal timescale decreases, which indicates that the behavior becomes more and more non-adiabatic. This is the star which is closest to the adiabatic limit, and this star should behave non-adiabatically, or in other words, for this star, we do not expect the adiabatic limit or the adiabatic approximation to be a good approximation. Maybe this star is described by the adiabatic approximation sufficiently well, but certainly these stars, the low mass stars, are not expected to be described by the adiabatic approximation. Well, together with the thermal timescale, also the fraction of gas pressure is found to vary with mass. So what we have here is the fraction of gas pressure, the ratio of gas pressure to the total pressure given as a function of the relative radius. Here we have the 50 solar mass object. It has the highest fraction of gas pressure, and the fraction of gas pressure within the envelope decreases as we decrease the mass. So this, the low mass star, has the highest fraction of radiation pressure, or this is certainly, the lowest masses are certainly dominated by radiation pressure. Again, so we deduce from that, first of all, these stars are probably not characterized or not described by the adiabatic approximation. They have a high fraction of radiation pressure, low fraction of gas pressure. So we might expect, if we refer to the mechanism for strange mode instabilities, we might expect, simply by the structure of this star, we might expect that we see strange mode instabilities in these stars, and that the adiabatic approximation should not work for these stars, simply by inspection of the properties of these stars. To finish with, we have here the adiabatic index as a function of relative radius for the various masses. We see that gamma locally, the gamma adiabatic falls below 4/3. Here, for instance, we have two places where gamma falls below 4/3. Well, what might be the cause of this minima or the low values of gamma adiabatic in these stars? When does gamma fall below 4/3? For instance, here and there. Well, these are the ionization zones where gamma falls below 4/3. But concerning the center of the star, we see that gamma is well above 4/3. And may I remind you of the definition of the mean adiabatic index. In the mean adiabatic index, in the definition, we have the pressure as the weight function. So the outer parts of the envelope do not have the same weight as the center, and so we may not expect from these, of course we haven't calculated this, but the outer part where gamma falls below 4/3, the low pressure part where gamma falls below 4/3 does not have a big weight, and we do not really expect from this figure that the mean adiabatic index falls below 4/3. So, well, keeping this in mind, we go back and we actually do a full non-adiabatic analysis for these stars, because we anticipate that the adiabatic approximation is not valid or does not give proper result. So we do a full non-adiabatic analysis of this sequence of stars. So in this diagram, we plot the real part of the eigenfrequency, the sigma r, as a function of mass for the various models. Let's start with the 50 solar mass objects. We have a nicely spaced spectrum. That's the spectrum we would expect for an ordinary acoustic resonator. Well, this star is the object which has the highest values for the thermal timescale, timescales. But once we decrease the mass and the star becomes more and more non-adiabatic, we see the mode pairing, mode crossing process here to occur below masses of, say, 30 solar masses. May I remind you, the mass estimated for ROCAS was 24 solar masses. Once we have thick lines, this should denote unstable modes. The thin lines denote stable modes. So what we see a kind of strange mode phenomenon. The modes pair and cross each other once we go to small masses, once we decrease the mass below a certain value. Okay, this is expected because we know that the thermal timescale decreases once we decrease the mass, and also the fraction of gas pressure decreases once we decrease the mass. That's what we have seen in the previous diagrams. Concerning the imaginary parts, well, here we start off with a more or less nicely spaced spectrum, and then below mass of, say, around 35, the first mode becomes unstable. Sigma I becomes negative, and if we decrease the mass even more, we observe that the eigenvalues seem to come in complex conjugate pairs or almost complex conjugate pairs. this is also some indication or some property we have seen for the strange modes. So we have a transition from a rather normal behavior to this strange mode behavior with instabilities appearing in groups or in pairs of complex conjugate pairs of modes. Okay, well, this is reminiscent of modes appearing in the NAR approximation in exactly complex conjugate pairs. So let's try an NAR approximation, at least for this part of the diagram of the modal diagram for masses below, say, 25 solar masses. In fact, if we do the NAR approximation for masses below 30 solar masses, we find the mode pairing process even in the NAR approximation. Here we have a mode pairing and depairing, so this is an instability bubble which we find here. And here we do not see the left-hand side of the instability bubble. So we get here mode pairings which lead to a pair of complex conjugate modes and thus to an strange mode instability. To complete this diagram, these are the imaginary parts. You see we have complex conjugate pairs of modes. Now let's superimpose the NAR approximation to the full problem to see whether the NAR approximation at least gives some feeling that this is the underlying instability mechanism. So we here as thick lines we have is the NAR approximation. Thick lines denote the NAR approximation. Thin lines denote the full problem, and you see that at least there is some similarity, or the full problem somehow is reminiscent of the NAR complex conjugate symmetry, and we see that the approximation is of course not quantitatively very good, but the qualitatively we may see that the onset here of the complex conjugate symmetry in the full problem is about the same as seen in the NAR approximation. So we see here NAR approximation is one of the possible, or NAR approximation may provide models based on the NAR approximation for this type of instability are promising to explain the instability of these yellow hypergiants. Again, let's see, 24.1 is the mass for rho cas, which is suggested. It's just at the beginning or the onset of the NAR instability. Okay, so we have solved now the full problem. Now we would like, of course, to know whether the conventional wisdom that these stars are get unstable due to the adiabatic index falling below 4/3, whether this is a possibility to explain the instability of these stars. So what we do is we calculate within the adiabatic approximation, we calculate the frequency of the first 3 adiabatic modes. May I remind you, well, once we have an adiabatic instability in the radial case, then this occurs through sigma squared becoming negative for the fundamental mode. So if we see instability, then we should see the instability to occur first in the fundamental adiabatic mode. The 3 lowest adiabatic modes are plotted here as a function of mass. What we see here, the fundamental mode does not go to 0, and it does not show any instability. So all these modes remain positive. Sigma squared of all these modes remains positive, so there is no adiabatic instability. We have explicitly calculated the fundamental adiabatic, and the first overtone, second overtone of the adiabatic spectrum, but these modes do not exhibit any instability. What does it prove? Well, in the first place, it proves that the mean adiabatic index cannot fall or cannot be below 4/3, because if the mean adiabatic value would have fallen below 4/3, then we would have an instability. This is the instability criterion. So actually, our impression about the run of gamma adiabatic and its mean, we are now sure gamma adiabatic, without having calculated this mean explicitly, because we don't see an instability. This means gamma adiabatic, the mean adiabatic index for these stars cannot have fallen below 4/3. And we do not see any adiabatic instability. And moreover, what you see once you compare the results of the full model, well, the full lines are the results of the full non-adiabatic analysis. What is the relation between the adiabatic result and the full result? Essentially, there is no relation. The spectrum of modes behaves entirely different in the adiabatic approximation and in the full problem. This was expected because we saw the thermal timescale. The thermal timescales are small for these stars, and we do not expect the adiabatic approximation to be a good approximation. This is seen here explicitly by comparing the results of the full analysis and the adiabatic analysis. There is no relation between these modes. There is not any of these, none of these modes has gets close to the adiabatic limit. So these adiabatic modes simply cross the other modes. There is no relation. This is to be expected because these stars are highly non-adiabatic, and moreover, there is no adiabatic instability. Well, to support this even more, we have done now a sequence in temperature. So we take a fixed mass of 25 solar masses. We take the luminosity of rho Cassiopeia as before, but now we change the parameter effective temperature, and we consider the stability of a sequence in effective temperature, and calculate the stability, the frequencies, the non-adiabatic frequencies as a function of effective temperature. This is the result. It's now a bewildering complex diagram showing strange modes coming up here. Thick dots again denote unstable models, and the thin lines correspond to the stable models. This, by the way, is the position of rho Cassiopeia. This is the temperature of rho Cass. We see this is full of strange modes. And, well, we have superimposed, of course, again our adiabatic modes. And even here, as a function of effective temperature, the lowest order adiabatic mode does not become zero somewhere, so we don't have an adiabatic instability, and moreover the adiabatic modes, the first two adiabatic modes, have nothing to do with the full spectrum. The adiabatic modes are not in any respect an approximation to the full problem. Well, consider the imaginary parts. Well, apart from a very small gap, which we do not know whether this is relevant or whether this is significant, the whole domain of effective temperatures from very high temperatures. These very high temperatures are temperatures which are appropriate, for instance, for luminous blue variables. From luminous blue variables through yellow hypergiants to red giants, all these stellar models are unstable except for this small gap, which we do not know whether it's significant. Apart from this gap, all stellar models are found to be unstable. But no instability, no adiabatic instability is found. These are all strange mode instabilities, and adiabatic instability does not exist. All these adiabatic modes, the fundamental adiabatic mode, stays well above zero. Okay, so this is, so to say, or maybe regarded as a summary and an example, a final example about adiabatic comparison of adiabatic approximations of strange mode instabilities and the properties of stellar models and the relevant properties to decide a priori which approximation might be valid and which approximation is not valid for these stars. And finally, the proof that our consideration of the background models and their properties are in agreement with what we find in the non-adiabatic and the adiabatic stability analysis. So this is a pretty recent study on the class of yellow hypergiants. Well, in some sense, it also extends to the luminous blue variables if we go to higher effective temperature. So with these remarks, I would like to finish with the chapter of considering the linear, adiabatic, non-radial, radial, and non-adiabatic stability, linear stability analysis of stars. And, well, considering the general strategy which we have followed for the study of the stability of stars and the description of pulsations, well, in the very beginning, I may remind you, we have started with the general strategy, which started with the construction of a hydrostatic model, the study of the linear stability, and then we had as a final point of the analysis, the final point of the analysis was given then as following, because the linear stability analysis cannot provide the amplitudes of the amplitudes of pulsations. The final point was then to follow, once we have found an unstable star, once the linear stability analysis has provided a model which is linearly unstable, to follow the evolution of an instability into the nonlinear regime and thus to determine the amplitude of the pulsation or to determine the final fate of an unstable star. And this will now be the last chapter which we want to discuss today. So we would like to switch now to the next file. And this chapter will deal with the nonlinear simulation of the evolution of an instability into the nonlinear regime, or in other words, with nonlinear pulsations. Well, first of all, I have to disappoint you. Well, one would like to do it, of course, also for non-radial perturbations. We have non-radial instabilities, but and one would like, of course, to account for rotation, magnetic fields, and all things like that, which are in their intrinsic nature three-dimensional, but this is not yet possible. The numerics and the numerical scheme, the numerical mathematics needed to do that is not yet in a state that we can perform the evolution or a simulation of the evolution of a non-radial instability into the nonlinear regime. So this is not yet possible. It's marginally possible to do a 1D simulation of spherically symmetric unstable perturbations into the nonlinear regime. This is possible, and the remaining part of this lecture will deal with the nonlinear simulation of spherically symmetric unstable perturbations into the nonlinear regime. Well, even for this case, we have to restrict our models, and we have to restrict our strategy. Well, as always in the past lectures, the outer boundary of the model will also be the photosphere. Any stellar model we have considered so far has as its outer boundary the photosphere. That means we do only consider the optically thick part of our star. Well, and the second drawback of all these simulations is similar to both to the stationary hydrostatic models, to the treatment of linear pulsation. Well, convection, we do not have a satisfactory treatment. But that's true for all kinds of treatments of pulsations. Well, and this is also true for the nonlinear treatment. For convection, we do not have a satisfactory treatment, and the only approximation or the only way how we could treat it is done as in the linear case. We adopt the frozen-in approximation, and we assume that even during the nonlinear simulation, the convective luminosity is assumed to be constant. The perturbation of the luminosity is 0. So these are the drawbacks. Outer boundary is not the outer boundary of the star, but it is the photosphere. And convection is not treated in a satisfactory way. Okay, so how shall we proceed once we do a 1D nonlinear simulation? Well, we start as outlined in the beginning. We will start from hydrostatic equilibrium. And we select a linearly unstable model. So we have taken a hydrostatic model, constructed a hydrostatic model, and we have investigated it for linear stability with respect to radial perturbation, and we select one of these linearly unstable models. Okay, so what we would like to have is then that we give the hydrostatic model to the code, to the nonlinear simulation code. Then, of course, because the model is linearly unstable, well, it should become unstable itself. So if we leave the model to the code, then we expect, for physical reason, if everything works nicely, that an infinitesimal perturbation, which is always present, will lead to the growth of the exponential growth of the linear instability. Okay, but once we do it, then it's disappointing. You will find either, depending on the code you are using, you will find two reactions on providing the model to the code. One possibility of reaction is nothing will happen. So this is the case once the simulation code is very dissipative, or it is dissipative. So it will dissipate energy once the instability will try to grow. So what you need then is an external perturbation. So you will shake your star, you will give it a kick, and then it might start to pulsate. The drawback here is, well, you don't know whether you see the instability or you do see the reaction of the star or of the code to your initial perturbation. So that's not what we want. We don't want to see the reaction of the code or the simulation on an external perturbation. The second possibility, depending on the code you use, is you immediately have a huge perturbation and the star starts to oscillate immediately. You have there are cases where you have to limit these initial perturbations, and some authors try to dissipate or to introduce an artificial viscosity to damp out this initial perturbation, which is not exerted externally, but which seems to be present even if we do not perturb it externally. So these two possibilities are both not that what we would like to have. What we would like to have is that the instability develops itself, and we want to see the exponential growth of the instability with the correct or predetermined pulsation period and the predetermined growth rate. Okay, so there is a problem to avoid either an initial perturbation which is inherent in the code or which is inherent in the procedure, or we also do not want to kick the model externally, because then we cannot be sure that we see the physical instability which has been predetermined by the linear analysis. The linear analysis gives us the frequency and the growth rate of the instability. That's, so to say, we want to verify or to validate the code and the linear simulation by seeing the linear phase of exponential growth of the instability. Okay, we don't want to have, or we don't want to apply an external perturbation, and we do not want to have an intrinsic perturbation from the beginning of the simulation. Okay, rather we would like to see the linear regime of exponential growth, and in the linear regime of exponential growth we want to compare the observed frequency and the observed growth rate with the linear result. Only then we can be sure that we are really simulating the evolution of the instability and not any numerical artifact. Okay, once we have saturation in the nonlinear regime, then we can determine the amplitudes and we can determine the final fate of the instability or the unstable model. Okay, now let's consider the initial model. Either we have high numerical dissipation. This requires no external perturbation. That's not what we would like. Low dissipation. Then we have initial accelerations in the nonlinear regime. The reason for this is that this is a possibility which we exclude from the very beginning. Here we might think, well, how can we improve this, and how can we get rid of these initial accelerations, and where do they come from? Actually, well, once we have the model which we start with is a model in hydrostatic equilibrium. So it satisfies dP by dmr minus dP by dmr minus gmr over 4 pi r to the 4 is 0. Okay, if it's not 0, and this is the case actually here, in this case it is not 0 in a numerical sense. So even if we construct a model which has these properties, it's not necessarily, this relation is not necessarily satisfied within the numerical scheme of the simulation code. The simulation code has a certain numerical scheme by which the gradients are to represent the gradients, and this numerical scheme need not be in agreement with the model which we prescribe as an hydrostatic equilibrium from other integrations we have done before. So what we have then is, this is d2r by dt squared. So if it's not in equilibrium, meaning it is not in equilibrium in a numerical sense, then we have accelerations, and these accelerations will give an intrinsic perturbation, and the model is not in equilibrium, and we have immediately big amplitudes of the oscillation. So how do we get rid of these accelerations? Well, we have to make sure that the model is numerically in equilibrium. That means we have to relax it or to recalculate the hydrostatic equilibrium using the numerical scheme which is used later on for numerical simulations. Okay, the reason is numerically not in hydrostatic equilibrium. Some authors increase the dissipation to get rid of these accelerations, but we favor here to calculate or recalculate the hydrostatic equilibrium of the initial model using the identical numerical scheme as used for subsequent numerical simulation of the evolution. In fact, that helps, and we can get by relaxation of the method of the model to hydrostatic equilibrium, we can get an initial value or an initial configuration which does not exhibit big initial perturbation or big initial accelerations, which immediately takes the star into the nonlinear regime. So we can, by this procedure, we can assure that we have a perfect hydrostatic equilibrium even with respect to the numerical scheme used. Once you compare the original hydrostatic model with the hydrostatic model obtained after relaxation, we will not find any difference. So it's just the numerics and small numerical changes which avoid these accelerations. So actually, if you compare the density structure, the pressure structure, and so on, you will not find any physically meaningful difference. So it's just a numerical problem. Okay, so let us see how the evolution of an instability looks like for a 45 solar mass massive stars with a single unstable mode. So we have a single unstable mode whose sigma values of sigma r and sigma I have been predetermined, and we are looking for the evolution of the velocity at the outermost grid point as a function of time. So these are the parameters of the star, and this is the evolution as a function of time. Well, we start at a level of 10 to minus 5 centimeters per second. This is the numerical noise from which we start. So this is very well in hydrostatic equilibrium, 10 to minus 5 centimeters per second. And what we see here, this is a logarithmic representation. So logarithmic representation means if we see a line, then this is an exponential behavior. This is the phase from zero. This is numerical noise. And here we have a nice linear phase of exponential growth of the instabilities. These vertical lines correspond to the zeros, so the distance of these zeros corresponds to the pulsation period. And if you take the slope of this, the envelope of these maxima, then we can derive the value of sigma I. So the growth rate can be derived by the slope of this line, and the values of the pulsation periods are derived from the distance of the vertical lines. And we can then compare these values for the period and the growth rate with the predetermined values of the linear analysis. And if they agree, then we can be sure that we follow actually the instability and not any numerical artifact. We have compared it, and of course we would not have presented this diagram if they would not agree. So this is a way to assure that you are simulating the instability and nothing else. What you see here then, after reaching a level of say about 100 kilometers per second, then the amplitude seems to saturate and remains constant, and we have a finite amplitude pulsating star. So in this way we have determined the final fate of this instability or the final fate of this unstable star, and we end up, and the final fate is finite amplitude pulsation. We derive the amplitude, and well, we derive the amplitude and we derive the final fate of the star. Finite amplitude pulsation is the final fate of this star. Okay, well, to summarize, numerical starts from numerical noise, linear regime, nonlinear regime. Well, I will show you in a moment how the well, we start off the linear regime means we have a we have an exponential of the time behavior will be exponential, or let's say, well, linear pulsation, which is a trigonometric function, steepens and forms shock waves in the final stage. The final velocity amplitude of the order of 10 to 100 kilometers per second, in this case, is about half of the escape speed of from the star. Well, we can also is originally due to the gradient pressure times the velocity, or which goes with the gradient with the divergence of the pressure times the velocity, and this can be transformed into a surface integral, and we have a surface surface element dA. This term occurring in the energy balance is the acoustic energy flux. So to say, this is the leaves the star through the photosphere. This is a non-monotonic function. It oscillates, but let's have a look. What is the energy which is transported mechanically? This is a mechanical energy. This is the mechanical energy flux, or the acoustic energy flux, through the photosphere of the star. So let's have a look how it looks like. Well, this is the final velocity profile of the star. Now we take just one period of the final finite amplitude pulsation, and you observe there are indications for shock waves. We do not have a nice trigonometric profile, but we have a sawtooth profile here for the final velocity of the order of 100 kilometers per second. Well, let's have a look for the final luminosity. This would be the light curve, which might be observable, so we could in principle compare this light curve with the observed light curve. This is one way how to connect the results with the observation. And there is the other, the term I was just talking about. Sorry for the bad quality. What happens? What is shown here is the run of this term of the acoustic flux as a function of time. So what happens here is we do not have a nice periodic function, but this function seems to increase with time. Well, there are phases where we have this flux increases with time, and then where it decreases with time, or this energy decreases with time. So this represents an outgoing flux. So we have a phase during pulsation where we have an outgoing acoustic flux, but then the acoustic flux reverses its sign. So the outer boundary moves back and forth, and we have phases of outgoing acoustic flux and phases of incoming or formerly incoming flux. But once we look on a longer scale, this is not periodic, and on the mean we have an outgoing acoustic flux from our star. So these are two pulsation phase, outgoing, incoming, but on the mean we have an outgoing acoustic flux, an outgoing acoustic energy, which we can calculate by simply taking the mean of this curve. And this accounts for this object, this accounts for 10 to 35 ergs per second. Do you know the luminosity of the sun? It's 10 to 33 ergs per second. So this is quite a big acoustic luminosity. And once we cannot determine the mass loss from this object because we stop our simulation is restricted to regions below the photosphere, but we know at the photosphere we have a mechanical energy flux of 10 to 34 ergs per second. If we suppose that this mechanical energy flux is transformed into a mass loss from the object, then we may ask, well, or may set it equal to the mass loss rate times the velocity at infinity squared. So the kinetic wind energy, if the kinetic wind energy is similar to the acoustic luminosity, then we will have acoustic luminosity should be of the order of mass loss rate times V infinity. Well, for V infinity, we have a measure. It's the escape speed from the object. We can calculate that. And if we take reasonable values for the escape speed of the star, then we can, by setting these two quantities equal, we can derive a mass loss rate. And the mass loss rate determined in that way usually amounts to 10 to minus 5 or 10 to minus 6 solar masses per year. So these are reasonable values once we compare it to the observed values. So in fact, this kind of pulsation may drive a mass flux from the object, which can be estimated on the basis of the acoustic energy flux our pulsation generates at the photosphere. Okay. Well, that's for the 45 solar mass star. Now let's consider a massive star with several unstable modes. Well, I've taken these massive star with one unstable modes to show you how you can compare the linearly determined eigenfrequencies with the results of the nonlinear simulation, and thus to how to validate your code. Well, once we take a massive star with several unstable modes, we cannot compare the linear regime with the linearly predetermined results and eigenfrequencies, and we will see another effect apart from that. Okay, so this is a massive star which has several unstable modes. These unstable modes are superimposed. They give on the mean some kind of a exponential growth. We start here with 10 to minus 6 centimeters per second, and well, this is a superposition of several unstable modes, so we do not get a nice straight line here, because these several modes with several periods and growth rates are superimposed here. But finally we get a similar result. Well, the amplitudes saturate here at a level of 10 to 7 centimeters per second. This is also 100 kilometers per second about. But once you compare the periods in the linear regime, periods are denoted here by the distance of the vertical arrow, vertical lines. Here they are much denser than in the final finite amplitude pulsations. So what happened here? The periods in the linear regime are not equal or are not related to the periods in the nonlinear regime. In the nonlinear regime, the period would correspond to the distance of these two vertical lines, of consecutive vertical lines. This is the finite amplitude pulsation, which is reached here. We know the amplitude now. but the period seems to have changed. What might be the reason for the change from the linear periods to the nonlinear periods? This star has a rather high growth rate, so it is strongly unstable. What has happened? Which quantity determines, or which quantity is responsible for the period in the first place? Once you want to know the period of pulsation of a star, what would you do in the first place? Pardon? Pardon? Yes, period density relation. There is a relation between period and density. So, of course, in the linear regime, the star satisfies the period density relation. Well, if the period becomes larger, what does it mean for the density? The density has to be decreased. So the mean density of the star has decreased from the linear or the hydrostatic value to the final finite amplitude pulsation domain. This means the mass, of course, cannot change. This means the radius has to become bigger. So actually, in that case of a strong instability, we do no longer expect the linear periods to be comparable to the nonlinear periods. What has happened? The instability has inflated the star. The star has become bigger. Shock waves traveling out have inflated the star, have given it a bigger radius, and as a consequence of the bigger radius, the period has increased, the density has decreased, and the period has increased. So it is not for, in particular, for strong instabilities, we expect the nonlinear periods to be different from the linear periods, whereas for weak instabilities, once the instability is not strong enough, the linear periods may be comparable to the nonlinear ones. May I remind you, usually people do only a linear stability analysis and compare the results of the linear stability analysis with the observations. This is true or can be done as long as we are sure that the nonlinear evolution will not increase the period by inflation of the star. So for weak instabilities, like a Cepheid, like the Sun and other stars, this is justified. We can compare the linear periods with the observed values, but for strong instabilities, such as strange mode instabilities in Wolf-Rayet star or in extreme helium stars, where we have strong instabilities, inflation of the star may lead to a significantly bigger period than the linear periods. So we have to be careful, and we have to do a nonlinear simulation for a comparison. Okay. Same is true here for a Wolf-Rayet star. To give you an example for the Wolf-Rayet star, also here we have the effect is not that pronounced, but in the linear regime we have a significantly longer period than in the linear regime of exponential growth. This is a Wolf-Rayet star here, and for the Wolf-Rayet star, to show you the spatial structure in the nonlinear regime, what you see here is the stratification of density. So what you see here in the inner part of the star, you don't see anything, but in the envelope of this Wolf-Rayet star, you see some consecutive waves exhibiting shock waves, or the shock waves in terms of maxima and edges or ridges in the density profile, whereas the temperature profile of the star does not exhibit any of these shock waves. The shock waves are isothermal shock waves. This is due to the fact that the thermal timescale is very small in these stars. It exhibits only density maxima or the counterparts of shock waves in terms of density maxima. These shock waves are also seen in the opacity. The opacity has a maximum exactly when the density is high. So we have peaks in the opacity which are related to the shock waves. This is the structure, the spatial structure of the nonlinear, of the finite amplitude pulsation of this star. Okay, well, now let's come back to the energy of the star. Well, we need to, okay, we have already talked about the fact that linear periods and nonlinear periods may differ, and for the Wolf-Rayet star we have also a significantly bigger nonlinear period than the linear period. The acoustic energy, as described before for the 45 solar mass star, is now of the order of 10 to 36 ergs per second, which amounts, or which gives a value of the mass loss rate of 10 to minus 6 solar masses per year approximately. Okay, now let's turn to the energy balance in a pulsation. What we need to have, or what needs to be satisfied for energy balance, is that the change of the sum of gravitational energy, thermal energy plus kinetic energy, plus the change, or plus the surface terms given by the thermal flux and the acoustic flux, is zero. So we have two surface terms. One is due to the divergence of the thermal flux, and this relates to a surface integral f times the normal vector of the surface times the surface element. So two surface integrals, they are denoted here with delta L thermal and delta L acoustic. Or we take the time integral of this of the energy balance, then the sum of gravitational, thermal, and kinetic plus the integral over the thermal energy plus the integral over the acoustic energy should be zero, or should be constant. Once you subtract the initial values, or the stationary values, it is zero. So what you have subtracted here is already the stationary or initial values. Now let's consider all these terms separately during the evolution of the nonlinear evolution of our pulsation. So this is a requirement, from the energy balance or the energy conservation law. Okay, well, what we are considering is whether this is actually true for our simulation, and it can be used to determine whether the simulation is accurate enough to satisfy energy balance and energy conservation. Let us consider the various terms now for the Wolf-Rayet star, which we have shown before. First of all, let's consider as a function of time the gravitational energy. This is the gravitational energy as a function of time. The green one is the internal energy, and the blue one is the integral over the luminosity. This is the surface term f times normal vector integrated over the surface of the star. Well, you see the biggest energy is gravitational energy, and the second biggest is the thermal energy. They behave quite opposite. They seem to cancel each other if we sum them up. And there is the third biggest energy, which is the integral over the luminosity. Well, if we sum up these terms, then we end up at the green curves. So summing up all these three terms, gravitational, thermal, and integral over the thermal flux, we end up with this green curve. So what we see here, that this green curve is at least 1 or 2 orders magnitude smaller than the energies which are involved in that sum. And also the kinetic energy is by 2 orders of magnitude smaller than the gravitational or the thermal energy. So if we sum up these two terms, then we have summed up everything except the acoustic energy flux. Well, then we have the following. Well, the energy flux, the acoustic energy flux of the acoustic energy is a periodic function, but on the mean an increasing function. This allowed us to determine the mass loss rate of the object. But if we sum up now kinetic energy, the sum of the previous energy and the acoustic energy, then we should end up with 0. So once we get a non-zero value, this is the error of the energy balance. So what we obtain then for the energy balance, we obtain an error of the order of 10 to 35 ergs, whereas the smallest energy appearing in the energy balance was this here with a magnitude of 10 to 41 ergs per second. Well, what you derive from this diagram is, well, if you want to have a meaningful result, well, we have up to 4 orders of magnitude difference in the energy terms. So if we make an error in the gravitational energy of only 1%, this error is as big as the kinetic energy. What we want to derive from our simulations is, of course, the magnitude of the kinetic energy. That's what we are interested in. The pulsation is essentially represented by its kinetic energy. And if we make an error in the gravitational energy of 1%, then we have this error is of the order of the kinetic energy, and our calculation is no longer meaningful. So we are interpreting errors once we are interpreting these simulations, and it may become as difficult as having up to 4 orders of magnitude in difference between the various types of energies. So that means we have to be very accurate in the determination of the energies. And what we have shown here is that actually the error here is 10 to 35. So this is by 6 orders of magnitude smaller than the smallest energy. So the results I've shown here are meaningful, but in general, you will not, for a general numerical scheme, you will not receive such an accuracy for the energy balance. Okay, first of all, what we deduce from that, the difference in magnitude of the various kinds of energies require an extremely accurate treatment, numerically accurate treatment. Otherwise, the error of the biggest energy would be of the order of the smallest energy, and the results would not be meaningful. Here we have shown that this accuracy requirement is actually satisfied. And the next question, of course, is how do we do it? How shall we guarantee that that we have an accuracy of better than 10 to minus 5. So for meaningful determination of the acoustic fluxes to determine the mass loss rates and the kinetic energies, that means the velocity amplitudes, an accuracy of better than 10 to minus 5 is needed. We have shown this is the case, so that's fine here. Well, that means that the energy balance needs to be satisfied by the numerical scheme intrinsically. You cannot achieve this accuracy simply by a refinement of the grid or by a refinement of the time integration. It can never be achieved by grid or refinement of time resolution. So you need to build in the energy balance into your numerical scheme. The numerical scheme has to satisfy the energy balance intrinsically. This is called a conservative numerical scheme, and these plots were to demonstrate and to convince you that you actually need such accurate schemes to simulate stellar pulsations. Okay, so in the next, I think we'll have a break. In the next lecture, the final lecture, we will see how this energy balance can be satisfied intrinsically, how how the numerical scheme is constructed to intrinsically satisfy this requirement. Okay, so we'll make a